You can begin when you're ready.
Okay, so hi everyone. Thank you for coming to discussion number 9. Okay, so let's start. Okay, this is outline for today's discussion. So first I have a couple of announcements about homework number 3 and midterm exam, midterm. Can you hear now? No?
Are you using the wireless mic or the desk mic? It is on and working.
Yeah, I think it's turned on, but...
It's on, we can hear you.
Okay. Can you hear me? No? Can you increase the volume? Okay. Okay, so this is outline for today's discussion. So I have a couple of announcements, and in the rest of the discussion, I focus on explain the perspective transformation and imaging geometry. So before starting the discussion, I have an announcement. So the due date of homework number 3 is coming Sunday. So please submit homework at least 1 hour earlier to avoid the unexpected network problem. And the midterm is will be held on the November 1st from 9 a.m. to 11:50. So actually, exam will be held conducted in 2 rooms. The one room is THH 301, and the other room is MRF 340. So for your information, I prepared a map. So THH is located at here, and the MRF is here. Okay? So student whose last name begins with A to Z should go to THH. And the other student whose name begins with N to Z should go to MRF. Okay? So please arrive 10 minutes earlier to the exam center. So here are brief midterm instructions. So basically this midterm is open book exam. So you can bring textbook, lecture note, discussion note, and your graded homework. But you cannot use a computer, mobile phone, internet. So for a calculator, you can only use one line calculator. So any kind of programmable calculator is not allowed. And also, on-campus students should bring your USC ID. And for then students, they can bring either USC ID or driver license. So there might be a session for TH to check your ID at the beginning. Okay, so let's start today's main lecture. So this is a recap of today's discussion, which is about perspective transformation and the imaging geometry. So you might encounter one problem in your midterm, which is about perspective transformation. So basically I assume that you are already familiar with basic transformations such as translation, rotation, and scaling matrices in both 2D and 3D. How many of you are not familiar with this kind of basic transformation? Okay, that's good. So today I will briefly talk about inverse transformation for the inverse wrapping, inverse transformation. And I'm going to explain the relationship between Cartesian coordinate system and homogeneous coordinate system too. And mainly I focus on the perspective transformation and imaging process. So on completion of this discussion, I hope you are able to explain inverse perspective transformation, and also you can learn imaging geometry where the world coordinate system and camera coordinate system, they are not aligned. Also, you can understand translations involved in such generalized imaging setup. So uncalibrated imaging setup. So I also give you an example. Okay, so in this figure, the so-called image formation, here the small x, y, z represent the camera coordinate system, and the capital X, Y, Z represent the world coordinate system. So in this figure, two coordinate systems are perfectly aligned. So for example, small x and capital X, and small y and capital Y, and small g and capital G, they are perfectly aligned each other. And there is one more term you need to know here, which is so-called the focal length. The focal length is defined by the distance from the center of the image plane to the focal point. So in this particular example, the focal length is given by a lambda. So the world coordinate of the focal length is 0, 0, lambda. So here, our goal is to find out the image coordinate, small x and small y, to which world coordinate x, y, z correspond. So again, we would like to find out the image coordinate small x and small y of corresponding world coordinate x, y, z. Okay, so actually you can find out the xy in terms the expressions of the xy in terms of capital X, Y, Z using some triangulation. So okay. So operator, can you switch to my notepad? Notepad. Can I have an overhead camera? Okay. So let me redraw this figure in more simplified version. So this is image plane, and this is capital Y and small y axis. And here is the center of the image plane. And there will be optical axis, which is nothing but Z axis, capital Z and small z. And suppose that we have a world point W, which will have a coordinate capital X and capital Y and capital Z. Point. Okay, so and at this point, passing through the focal point, camera lens, and will be projected onto image plane. So this point C is expressed by small x and small y. Then in this configuration, we have two similar triangles, so we can use a triangulation. So in terms of the y-axis, this is a plus direction and the minus direction. So this distance will be minus y, and focal length is given as lambda, and this distance will be z, and capital Y. So we can derive following equations. So minus y, small y, over lambda is equal to capital Y divided by this distance will be capital Z minus lambda. So Z minus lambda. So this is nothing but y is equal to lambda capital Y divided by lambda minus capital Z. So similarly, we can find out the x coordinate, small x coordinate, in terms of the capital X, Y, Z. So which will be lambda x, capital X, divided by lambda minus capital Z. So these are two Cartesian coordinates of the image of the point on the image plane. So now we can also express xy as a matrix expression in terms of the homogeneous coordinate. So this is a Cartesian coordinate, but now we are trying to convert this Cartesian coordinate to the homogeneous coordinate. Okay, so how do you do that? So first of all, you need to know the way how to convert Cartesian coordinate to its corresponding homogeneous coordinate. Actually, it's very simple. You just multiply xyz component by any non-zero constant k. So in this case, if we convert this Cartesian coordinate to its corresponding homogeneous coordinate, which will be kx and ky, kz, and the k will be appended to the last component. So this is the homogeneous coordinate of this Cartesian coordinate. And also, homogeneous to Cartesian coordinate conversion is very simple. Just divide 3 components by the last component. Then abandon this last component. Then you will get back your original Cartesian coordinate. Okay? Yeah. So we can also express these 2 coordinates with the vector form, which will be W is equal to capital X, Y, Z as a column vector, and WH, here H means the homogeneous coordinate. So the homogeneous world point can be expressed by Kx, Ky, Kz, and K. Okay, so now we define so-called perspective transformation matrix P. This is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, minus 1, over lambda 1. So basically, if you multiply this perspective transformation matrix P by WH, WH is a homogeneous world coordinate, then final output you will get is corresponding homogeneous image coordinate. Can you follow me? Okay, so what's WH? What is the WH? WH is a point in the world coordinate system in terms of homogeneous coordinate. So now you are trying to transform from 3D to 2D. So this is the point in the 3D world coordinate system, and CH is the corresponding projected 2D point, but in terms of the homogeneous coordinate. Okay? So your corresponding, okay. I'm sorry? Okay. Operator?
Yes.
Yeah, can you use that large screen for the computer screen? Okay, so these are our homogeneous coordinate for the points on the image plane. So element of CH are the camera coordinates in homogeneous form. Now we are trying to convert this homogeneous coordinate to its corresponding Cartesian coordinate. How do you do that? I just explained in previous slide. What is the rule to convert homogeneous coordinate to corresponding Cartesian coordinate? Yeah, so you can just, okay, so operator, can I have a overhead camera? Okay, thank you. So here, so now we would like to find out the Cartesian coordinate, C. So for example, think about the X component. So how do you find out Cx in terms of a Cartesian coordinate? So we simply divide the first component X, Kx, by the last component k g minus lambda plus k. So this will be k lambda k minus kz and kx lambda kx k minus kz. So k can be cancelled out. So the final output is lambda x divided by lambda minus c. So this expression. So you can calculate similar cx, cy in a similar way. Okay, so Cartesian coordinate small x and small y can be expressed like this way. So these are the coordinates on the image plane of the projected 3D point x, y, z. But any point on the image plane, we don't need the z-axis, because on the image plane we only have two axes, x and y. So here we don't need the z-axis, so z is of no interest now. But actually, this g component will act as a free variable in inverse perspective transformation. So I'll explain this in the later slide. Okay, so now let's think about the inverse transformation from 2D to 3D. So previously we transformed a point in the world coordinate system to the point on the image plane. So now we are trying to map back the point on the image plane to its corresponding world coordinate point. So in order to do that, you need an inverse perspective transformation. So I just gave you here P inverse. The only difference from P is we just took out minus sign from this component. Okay, so using this equation, we can map back the point on the image plane to the corresponding world coordinate WH. So suppose that we have a specific image point x0, y0, 0 on the image plane, and this is its corresponding homogeneous coordinate. Then if we apply, if we using this equation, we can find out WH. WH will be kx0, ky0, 0, k. Then if we convert this homogeneous coordinate to its corresponding Cartesian coordinate, it will give us x0, y0, 0. But is this result correct or no? Correct or not? Yeah, this is not correct because it gives us g value always 0. But it's not possible. This is a point in the 3D coordinate system, so it should have a certain value for g component. But now we have we are having 0 for g component. So this result is unexpected, also not acceptable because it gives g is equal to 0 for any given 3D point. So what is the problem here? Sorry? What is the reason for this kind of weird result? Okay, so if we go back to this figure, so if you take a look at this figure, actually from 3D to 2D transformation is not one-to-one mapping, but it's a many-to-one mapping. So for example, all the points on this line are mapped to the same position here, x, y. So this is the reason for the wrong result. So how do you tackle this problem? So again, the problem is that mapping of 3D scene onto image plane is many-to-one mapping. So x0, y0 is the mapping of the point on the straight line passing through focal point and the projected image point. So instead of getting the specific point in the world coordinate system, we will get an equation for the line, straight line. So if we do the transformation from 2D to 3D, the final output will be an equation of the straight line instead of the specific point. Okay? So inverse perspective transformation is formulated by using G component of CH as a free variable. So instead of assuming the C component is equal to 0, now we assume G component of the CH can be a free variable. So we are using G as a free variable. So if we apply this inverse transformation, we will get this kind of homogeneous form for a point in the 3D coordinate system. So now we have a kx0, ky0, kz, and kz over lambda plus k. Then again, we convert this homogeneous coordinate to its corresponding Cartesian coordinate. And if you see this if you see the last line, you can derive the g is equal to lambda small z over lambda plus small z. After rearranging this equation in terms of the small z, we can solution into these two previous equations. Then we will get the expression for capital X and capital Y in terms of the capital Z. Right? Yeah. So again, the 2D to 3D transformation will give us an equation for line instead of a specific point. So if you want to find out corresponding void point, at least you need to know the Z information. So if you know the Z information, Z value, along with these two equations, you can find out the exact position in the world coordinate system. So do you have any questions so far? You need to know this to solve one of the Newton problem. Okay? Okay, so now let's take a look at more general case, more generalized situation. So everything we have discussed so far is based on the assumption that two coordinate systems, the camera coordinate system and the world coordinate system, they are perfectly aligned, right? So now we are take a look at more generalized situation where the world coordinate system and the camera coordinate system, they are not aligned. So here is an illustration. So in this figure, again, small x, small y, small z represent the camera coordinate system, and capital X, Y, Z represent the world coordinate system. So they are not aligned in this figure. So more concretely, okay, so let me explain. So this camera is mounted onto gimbal. This is called the gimbal. And using this gimbal, you can pan the camera by the angle theta with respect to z-axis. You can also tilt the camera by the angle alpha with respect to the x-axis. And finally, there is a displacement between gimbal center and the center of the image plane. So this is the general situation. So again, our goal is to find out image coordinate xy to which world coordinate xyz correspond. Okay? So given a point W, the world point W, x, y, z in the world coordinate, how do we find the corresponding image point C, x, y, small x, y? So this can be done using this two-step algorithm, two stages. So in the first step, we will bring the camera and the world coordinate system in perfect alignment by applying a set of transformations. After finishing this transformation, we simply apply the perspective transformation to get the corresponding image point coordinate for any given world coordinate. Okay, so let's take a look at each step more closely. So in the first step, we need to apply a set of transformations to make an alignment between two coordinate systems. So actually, we need to apply following 4 transformations, one after another. So here, remember that our starting assumption is that two coordinate systems are perfectly aligned. That's our starting assumption. Then we apply, then we displace the gimbal center from the origin of the world coordinate system by the vector W0. After that, we pan the camera by the angle along the z-axis. After that, we again tilt the camera by the angle alpha with respect to the x-axis. And finally, we will displace the center of the image plane with respect to gimbal center by vector r. Okay, so this is first step. So as I mentioned just before, at the beginning we assume that two coordinated systems are perfectly aligned. And now we are trying to displace the center of the image plane of the camera by the vector r from the center origin of the world coordinate system. So if we transform this camera from the origin of the world coordinate system by vector W0, all the 3D points will be shifted to minus W0 in terms of the camera coordinate system. So I'm saying here we are focusing on the coordinate with respect to camera coordinate system. So if we apply this displacement to the camera from the origin to here, after this transformation, the coordinate of the world coordinate of the point in the 3D world coordinate system will be shifted to the minus W0. Do you understand? Yeah. So if you are familiar with the translation matrix, this is actually unified translation matrix for the 3D case. So your transformation matrix will be 1, 0, 0, minus x naught instead of x naught, 0, 1, 0, minus y naught, 0, 0, 1, minus g naught, and 0, 0, 0, 1. Okay, let's move on to second step. Second transformation. So now we are going to pan the camera by the angle theta with respect to z-axis. So if we pan the camera with respect to z-axis, the z value doesn't be changed at all. Only x and y value are changed, right? So these are the rotation metrics for that. So actually in 3D case, there are 3 different rotational metrics. Do you know that? Yeah.
In the previous slide, how is minus x naught? Isn't it supposed to be plus?
Okay, so now we are focusing on the coordinate in terms of the camera coordinate system. So at the beginning, two systems are perfectly aligned. So the coordinates are the same between two coordinates. But now we displace this camera from the origin of the world coordinate system by the vector W0. So if you see any point in the world coordinate system, it will be shifted by minus W0. Okay. Yeah, that's why I put minus sign here. Okay. Yeah, everything is with respect to camera coordinate system. Okay. So again, so in this case, we apply the rotational transformation with the same vector theta, but in opposite direction. So basically, the rotational matrix R theta is defined by cosine theta, but cosine minus theta is just cosine theta, right? And the minus, here is the original expression for this part is minus sine theta. But here we put minus theta here. So minus sine minus theta is sine theta. And the cosine minus theta is minus sine theta. Cosine minus theta is cosine theta. So this is our rotational matrix for panning. And after that, we are going to tilt the camera by the angle alpha with respect to x-axis. Okay? So this is the rotational matrix for that. And finally, okay, so far we have got three transformation matrices. One translation matrix and two rotational matrices. So we combine these two rotational matrices, R alpha, R theta, to generate one single matrix R. Okay, so this is unified rotational matrix. The last transformation is to displace the center of the image plane from the gimbal center by vector R. So as we did in the first transformation, you can derive this translational matrix T minus R1 minus R2 minus R3. Do you have any questions so far? Okay, so now a homogeneous world point WH will be mapped to a homogeneous image point CH as given by the transformations. So, yeah, why the H is here? So here, there are four matrices, P, T, R, Z, but T, R, Z is for the transformation matrices to make the alignment between two coordinate systems. So if you apply TRG matrix to this homogeneous world point, you will get transformed 3D point with respect to camera coordinate system. Okay? After that, by simply applying P matrix, you will get corresponding image coordinate in terms of the homogeneous coordinate. Okay. So again, so this is a homogeneous coordinate system. So you can convert this to its corresponding Cartesian coordinate. So this will be your final expression for small x and small y. Okay? It's not that difficult actually. So I'll give you an example about this topic. So basically in this example, we assume that the center of the image plane of the camera is located at 0, 0, 1 with respect to 3D world coordinate system. So the center of the image plane located here, 0, 0, 1. The question is that what will be an image coordinate of the world coordinate 1, 1, 0.2. And following informations are given. So tilting angle is given as 135 degree. And the panning angle is also given as a 135 degree. And the focal length is given as 0.035. Okay, so operator, can you switch to my notepad? Can I have the overhead camera? Operator? Okay. So, okay. So at the beginning, the camera coordinate system and the world coordinate system, they are aligned. So our first transformation will be to displace the camera from the origin of the world coordinate system by the vector W0. So in this case, in this problem, the world coordinate is given by 1 point. 1 comma 1 comma 0.2, and okay, so this is camera, and here the center of the image plane will be located 0 comma 0 comma 1, right? So first we need to find out the transformation matrix for this displacing. So we already derived it in the previous slide. This is our translational matrix, right? So here x naught is equal to 0, and the y naught equals 0. Z naught is equal to 1. So our Z matrix will be minus 1. 0, 0, 0, 1. So we got our translational matrix Z here. Okay, so this is a step 1. Step 1 is for the translation. And in step 2, we are going to pan the camera by the angle 135 degrees. So step 2. Step 2, we are going to pan the camera by 135 degrees. Okay, so let me draw two-dimensional plane. So this will be x-axis, capital Z, capital y-axis. So now we are trying to pan the camera along the z-axis by the 135 degrees. So this is our new x-axis. Usually the usual custom is anti-clockwise direction. But actually you don't need to care about the yeah, the axis like this. So this anti-clock direction is the forward direction. So y-axis. So okay, so again we already known that this r theta matrix here. So you just need to put 135 degrees to the theta. That's it. So r theta cosine 135, sine 135, 0, 0. 1, 0, 0, 0, 0, 1. Okay, so step 3 is for tilting. Tilt the camera by 135 degrees. So let me draw 2D figure again. So in this case, maybe, yeah. So this is y-axis in terms of the world coordinate system. And this is xy plane. And the camera is tilted by 135 degrees, right, this way. Okay, so our rotational matrix R theta will be 1, 0, 0, 0, 1, cosine 135, sine 135, 0, 0 minus sine, yeah. Which one? 135. This one? No, it's the y. Oh, yeah, z. I'm sorry. Yeah. the z-axis, I'm sorry. And cosine 135, 0, 0, 0, 0, 1. Okay, so in step 4, now we can find out the transformed coordinate of w, 1, 1, point 2, which is seen by the camera coordinate system. So let me just write down here. So now we are going to find out transformed 3D coordinate of 1, 1, point 2, which is seen by camera coordinate system. So how do you find out the coordinate of the transformed 3D, transform the 3D coordinate of the original world coordinate? We already found out every transformation matrix. So we can just apply transformation one after another. Okay, so transformed X and transformed Y, transformed Z. So our original world coordinate is 1, 1, point 2, and 1. Because of this is the homogeneous coordinate. So if you calculate this formation, unified transformation matrix, it will be minus 0, 7.7, 0.700, 0.5, 0.5. And so if you solve this matrix multiplication, you will get transformed 3D point as 0.43, 1.55, 1. So this means 0 and Y and Z. So this point is as seen by the camera coordinate system. Okay, so now the last step is to find out the image coordinate of the original 3D point by simply applying the perspective transformation to this transformed coordinate. So, okay, so just write down here. Step 5. In step 5, we are going to find out image coordinate of the original 3D point. How do you do that? By applying perspective matrix P, right? But we already derived the following expression in the previous slide. So if we apply the perspective matrix to any point in the 3D world coordinate system, the x-axis, the Cartesian coordinate for x-axis will be lambda capital X hat divided by lambda capital Z. And for y, we can write down lambda capital Y divided by lambda minus d. So we know that lambda is equal to 0.035. So we can calculate these two values, which will be equal to x. X will be equal to 0, and the y equals to 0099. So these are final output of this problem. Okay.
What does the small letter r correspond to in this example?
Small r.
Yeah.
Small r. Okay. Here. This r.
Yeah.
That is nothing but the XYZ component of the displacement from the gimbal center to the center of the image plane with respect to 3D world coordinate system.
What is it in this example?
This example, okay, so this is just a unified expression, but I split the process into several stages now. So, in this case, there is no R. So in this example, there is no displacement between image plane and the gimbal center. Yeah.
So when do we decide when we should determine the R or when we shouldn't determine the R?
Oh, that's because in this example, there is no gimbal. Yeah, so you don't need to care about gimbal. Yeah. Okay, so that's all for today. I prepared. So there is one problem in the midterm about the perspective transformation. So if you are familiar with all these equation transformation, yeah, you will be fine. Yeah. Okay, thank you.
This concludes E569 discussion on Tuesday, October 29th, 2013.
The time is 9 o'clock.